Hello, everyone, and welcome to our talk, Cracking the 5G Fortress, Peering into 5G's Vulnerability Abyss. Please allow us to briefly introduce ourselves. I'm Kai, and I'm a PhD student from SynSec Lab at Penn State University.
Hi, I'm Ilu, and I'm from the same lab as Kai.
Okay, thanks, Ilu. So, as you all know, 5G network is everywhere. We use it for many small daily tasks, like watching a TikTok videos or call Uber when you need a ride. Due to its ultra-low latency and more capacity, 5G is also deployed at a massive scale in autonomous vehicles, cyber-physical systems like factories and power plants, which previous generations of networks are not capable of. In such a 5G ecosystem, 5G basebands are the key enablers. Devices equipped with 5G baseband can seamlessly connect to the 5G networks and support critical applications, such as manufacturing units control, autonomous vehicle-related communication, those kind of things. While these applications highlight the power and potential of 5G, they also underscore the importance of ensuring the security of 5G basebands. It's easy to understand that if the baseband got compromised, user will run into critical problems, like their information could got leaked, they could got phishing messages, or their service may got disrupted at any time. From another perspective, if a 5G device are compromised, it may not only affect the device itself, it may also serve as the entry point for more malicious attacks targeting on other components in 5G networks, for example, the base station or the core networks. As a researcher in this field, we understand the importance of securing the baseband. Back to 2 years ago, when we initially set up our research project, no open source 5G user equipment testing framework was available. Even the open source 5G protocol stack is in the beginning phase. But we are curious to find out the answer that how secure those 5G devices are, and whether we can develop an automated way to test them. So in today's talk, we would like to introduce you to some 5G background information first. Then we will explain how we come up with the idea of automated 5G baseband testing tool, 5G Base Tracker, and how it works. After that, my colleague Ilu will summarize our findings and show you the most exciting part of today's talk, the 5G aka bypass attack demo. We will show you 2 end-to-end vulnerability exploitation demos. Finally, we will discuss the impact and the status of our research, and I will leave you with some key takeaways. Okay, here we have a simplified diagram of 5G network. This is a pretty high-level architecture. The left-hand side is a UE, which is a user equipment. You can understand this is a phone. It will connect to the G-Node B, which is a base station, via the radio. Then we have a 5G core network, which is behind the G-Node B, the base station, and serving as the backbone of 5G network. The 5G core network contains many network functions. This figure only contains the main components that are related to our talk today. As you can see from the figure, the first component is the AMF, which is Access and Mobility Management function, which is responsible for handling UE registration, connection management, and mobility management. More importantly, this component also manages the security-related procedures. Okay, we also have another component, UDM, which is basically a database, stores the user's profile and some subscription data. After that, we have a SMF, which is a session management function, which handles establishing or releasing the data sessions. Also, we have another one called UPF. It's a user plane function. It's responsible for forwarding the user data packets and applying some traffic rules. Basically, it's doing routing. Before the phone actually gets any service, such as accessing the internet or making a phone call, it has to be registered with a 5G core network as a valid user. During the registration procedure, the phone will first establish the radio connection with the base station. Then several security-related procedures will occur, such as the authentication procedure, the core network will authenticate whether this phone is a valid user or not. And then the security mode control procedure will happen, and also the AS security will be activated. These two procedures ensures that the further communication between the phone and the network is ciphered and also integrity protected. After that, you are able to get some services, and it's secure. So if the registration procedure were executed properly, the UE should have already established secured communication channel between the network. More precisely, it's between the user equipment and the AMF, and also between the user equipment and the G-Node B, the base station. The scope of our work is trying to identify the logical vulnerabilities in 5G user equipment's control plane. In other words, the NAS and RC layer in 5G protocol stack. The logical vulnerability here, we mean that, for example, whether there exists any critical flaw that could lead to authentication bypass, or error handling some messages which could lead to some undesired behaviors. In other words, we are trying to identify the protocol implementation flaw instead of detecting those memory corruption-related bugs. Okay, now some of you may be curious. The specifications are there, and the baseband vendors are following the guidance to build their product. Why could the baseband go wrong in this case? Actually, the reality is a bit more complex than the imagination. Implement such a big 5G protocol in baseband is actually very challenging because the specifications provided by 3GPP consist of hundreds of documents, and also each document may contain hundreds of pages. On top of that, the specifications sometimes contain incomplete or conflict information. This made developers facing difficulty in understanding and implementing the whole system. So it's actually very hard for the developers to implement the baseband without any mistake or flaws. However, those implementation flaws, in other words, failure to comply with the specifications, may result in security and privacy issues. These non-compliant behaviors are plausible areas of vulnerabilities, and either leads to exploitable attacks or interoperability issues. So here comes up our research question. Is it possible to develop an automated framework to identify those security policy violations in 5G UE implementations? To achieve this goal, we designed our tool, 5G Base Checker. The key intuition is differential testing. Since those 5G devices are implementing the same protocol, if two devices behaving differently for the same input, then at least one device is non-compliant with the specifications, or this is a case that underspecified in the specification. Building on this intuition, 5G Base Checker applied differential testing on multiple 5G devices to identify deviant behaviors. After that, we use those deviant behaviors as a proxy for identifying potential security violation in those 5G devices. Since we are doing differential testing, one question would naturally arise here: how to generate the input? Generating random inputs will not work because 5G control plane protocol is actually stateful. And also, we are doing over-the-air testing. This is a bit slow, and if we generate random inputs, it will take a lot of time. So we need a smarter way to generate the input sequence instead of randomly generating them. We decided to utilize automata learning technique to synthesize finite state machine to model each device's behavior and then identify the differences between those constructed finite state machines. Okay, next I will introduce how our tool, 5G Base Checker, works. So we have three components: the state synth, dev scan, and devlizer. I will introduce these three components sequentially. Okay, now let's move to the first component of our tool. It is called state synth. The input for this module is a set of 5G UE implementations, and the output is a set of corresponding finite state machines. We also proposed a very cool technique called hybrid and collaborative learning technique, which significantly improved finite state machine learning efficiency. We can bring it offline if you are interested in our approach. We construct the finite state machines for all the devices sequentially until we construct finite state machines for all the devices. Then let's move to the second component, DevScan. After constructing finite state machines for each device, we start identifying deviations between them. DevScan takes all extracted finite state machines as input, reduce the problem to a model checking problem, and check the property that, given the same input message sequence, whether two finite state machines are giving different output. To capture all unique deviations, we also introduce the graph traversal algorithm here, which means that if an attack could be launched in multiple ways, our tool DevScan can also detect those. After obtaining those deviations, we absolutely need some other techniques to help triaging the deviations. For example, identify whether a deviation violates any security property or not. So we designed the third component. We call it DevLizer. Initially, all the deviations in the set, we mark them as unresolved. The DevLizer first picks an unresolved deviation, then provide it to the security expert for manual analysis. The security expert then searches the 5G specification to identify the correct behavior for this input sequence and write one or more LTL property, then return those properties back to the DevLizer. Based on those LTL properties, the DevLizer can automatically triage a set of deviations. And the security expert will work with the DevLizer iteratively, keep adding some LTL properties into it until all the deviations got triaged. This is the full pipeline of our tool, 5G Base Tracker. Now my colleague Ilu will summarize what we have found and show you the end-to-end vulnerability demos. Let's welcome Ilu.
Thanks, Kai, for his great introduction about our tool, 5G Base Tracker. Now I want to give you a summary of the vulnerabilities we find in this project. So in total, we find 13 vulnerabilities in 17 devices we tested with these 5 different baseband vendors: MediaTek, Samsung, Exynos, Qualcomm, Unisoc, and HiSilicon. In addition, we tested 2 different open source 5G stack implementations. In these 13 vulnerabilities, we find 3 types of flaws and 4 types of impact. I will explain them one by one. And after the flaws and impacts, I will give you the most excited part of our talk, the 5G AKA bypass attack demo. Now let's start it with types of flaws. We find that in some baseband implementations, it will accept invalid security header types. And also in some other implementations, it will accept message types that should not be accepted in a certain state. Since the 5G protocol is stateful, there is only a subset of the messages can be accepted in the specific state of the protocol. Also, we find that some other baseband implementations mishandles the information element. To better understand this kind of messages, we provided this 5G control plane message structure. So here at the left, we have the RRC message, which handles the RRC protocol between the phone and the base station. Also, NAS messages between the phone and the core network is encapsulated inside the RRC messages. Inside these messages, we have different fields. We have message type, which I discussed before, and we have security header type, which controls the integrity protection and the ciphering algorithm of this particular message. Also, we have different information elements for the protocol use. Now I want to introduce the 4 different types of impact we find. So the first one is information leak. We find that an attacker is able to monitor the user traffic between the phone and the base station. Also, the second one is phishing. So the attacker is able to send a phishing SMS from the attacker-controlled fake base station to the phone. The third one is downgrade attacks. So the attacker can craft a specific message to force the phone from a more secured 5G connection to the less secured 4G or even 3G radio connection. Also, in the last, we have denial of service. The attacker is able to interrupt the user's service for a certain period of time. Now I want to introduce the most impactful attack we find, the 5G AKA bypass. So by 5G AKA bypass, we mean that the attacker is able to bypass the 5G authentication and key agreement procedure. We find the attack in Samsung X noise basebands. And in this attack, no mutual authentication between the phone and the network will be established. Also, since there is no mutual authentication, the attacker can just provide services to the user from a fake base station. For example, the attacker can just send SMS and also provide internet access to the phone. Next, I want to briefly introduce about the 5G registration procedure. So first, to connect to the network, the phone needs to send a registration request message to the network. And then we have the authentication procedure, which mutually authenticates the phone and the network. Next, we have the security mode control procedure, which will select the ciphering and the integrity protection algorithms for the following messages. After those two procedures, we will have a secured connection. In this case, the next message is the registration accept message from the network to the phone, and also the registration complete message from the phone to the network should be ciphered and integrity protected. Next, the phone will send PDO session establishment request message to the network to establish a PDO session for internet access, and the network should accept this message. After all these procedures, the phone will have internet access. So in our 5G AKA bypass attack, we find that the attacker can set up a fake base station which lures the user to send the registration request to. After it receives the registration request message, the attacker can send the registration accept message directly to the phone with security header type 4. So for security header type 4, it means this message should be both ciphered and integrity protected with new 5Gs context. However, here we just send the plain text registration accept message. In addition, this security header type 4 should only exist in the security mode complete message sent from the phone to the network. After that, the phone will reply with a registration complete message to complete the 5G registration. In this case, we bypass the authentication procedure and also security mode command procedure. So we don't have the secure connection between the phone and the network, and all the following messages are not integrity protected and ciphered. In this case, the attacker can just craft any attack message and send it to the phone. Now I want to show how we can get internet access from a fake base station to the phone. Here we have the 5G AKA bypass attack we discussed before first, and then the phone will send PDO session establishment request message. Our attacker in this case will send PDO session establishment accept message, also with security header type 4, to the phone. We exploit different vulnerabilities in order to craft this message. So let me show you how our attacker will create this kind of attack message. Here we have the PDO session establishment accept message first. It is required to establish a PDO session from the network to the phone for the internet access. After that, we encapsulate this PDO session establishment accept message into the downlink NAS transport message with security header type 4. So we exploit the same vulnerability we use in the 5G AK bypass in the registration complete message. In this case, the phone will accept the whole NAS message. However, this is not enough for us to give the phone internet access. We need to encapsulate the whole NAS packet into the RC reconfiguration message with the specific information element, DRB to add mode list. So here, actually, we exploit another vulnerability we find. Since the RC reconfiguration message with this kind of specific information element should not be accepted in plain text. But also we find the specific baseband can accept this message in plain text. Here we have our attack message. Next, I want to discuss about the setup of our attacker. So we are using software-defined radios. In our lab, we have the USRP B210. For the software, we are using open source implementations of the 5G stack. We have OpenAI interface serves as our base station, and Open5Gs serves as our 5G core. Now, let me show you the demo of our attack. So in the middle, as you can see, we have the phone. We have the 5G phone and a fake base station set up. In the left, we have the two terminals. One is for base station, and another one is for the 5G core. And also, we capture the traffic between the phone and our fake base station. As you can see here, at this step, the phone sent registration request message to the network. And our fake base station attacker sent the plain text attack message. And at this point, the authentication procedure and security mode control procedure is already being bypassed. After that, as you can see, from the attacker's point of view, there is plain text DNS packets flowing from the phone to the attacker. In this case, from these plain text DNS packets, the attacker can infer which websites the user is browsing. Also, the attacker will have the capability to modify these DNS packets to launch DNS hijacking attacks. That will redirect the user to some phishing websites. As you can see here, the user is able to browse the internet and also watch YouTube videos. Our attack is completely transparent to the user. So there is no notifications from the phone, and the user is completely unaware of this kind of attacks. Yes, you can see we can provide smooth connection between the attacker-controlled fake base station and the victim device. Now, let me show you the second attack demo we exploit. So here we have the phishing SMS injection. After the 5G AK bypass attack we discussed before, the fake base station attacker can also send me send the downlink NAS transport message with phishing SMS to the user. So here comes our second demo. As you can see, the setup is the same as the previous video. And this time, the phone is connected to our fake base station, and the authentication is bypassed. So from that downlink NAS transport message, the fake base station attacker sent an SMS to the phone with customized number and customized content. That means the attacker can just impersonate as some government agency to send a phishing SMS to the user. Next, I want to talk about our disclosure status of the vulnerabilities we found. So we reported all the uncovered issues to the corresponding baseband vendors. And we get 12 CVE numbers in total, listed here. Also, our work is acknowledged by the GSMA. Now I want to hand it back to Kai to let him finish our talk.
Yep, thanks, Ilu, for the attack demo and presenting the disclosure status. Now, let's wrap it up. To summarize, here are some key takeaways that we want to convey. The first takeaway is that we feel more security-related tests are required before shipping those modern products into the market. We know that there might be some conformance testing before the vendors put the modern product into the market, but actually this is not enough because we can still identify many flaws exist in those commercial products. And we feel black box testing is an efficient method to detecting those logical vulnerabilities because it only requires input and output analysis, making it more scalable and more convenient when comparing to those emulation or rehosting-based approaches. We also open sourced our tool, 5G Base Checker, at GitHub, so it should be fun to play. So thank you so much for attending our talk today. And feel free to reach out to us if you want to discuss more or have any questions. Thank you very much.
Thank you so much.